Okay, we've got the 2008 differential equation FRQ question. First part of this question is nice and easy. We are just going to put in the solution curve for two given points. So the first point they're having us look at is 3, 2. Super nice. They actually gave us the point on here. And then all we're going to do is we're going to follow the flow of the slope field. So we'll go up, and it definitely levels off right there. There's a kind of get the effect of a horizontal asymptote through that spot, and then we'll come back down over here. So that would be a good example of that solution curve. We'll do the same thing for the 0.08. Again, they give us the point. Now this one is just, it goes down and then it levels off at 6. And that one's going to come up again in question D. But if we got both of these, this is a 2-point question, 1 point for each of those curves. So that should be like, those are like free points. All right, moving on to question B. Said use Euler's method starting at t = 0 with 2 steps of equal size to approximate f of 1. So this gives us all the information we need to start an Euler's method table. So remember, we want to make sure we have those 5 columns, x, y, y prime, delta x, and delta y. Tough thing to remember here is that delta y is equal to y prime times delta x. Now, the starting point. Starting at t = 0. So at t = 0, if we look back at the start of the problem, t = 0 is given here as the point f of 0 = 8. So 0 is our first x, technically t in this case, but our first x, and 8 is our first y. And then we're going to use this differential equation to help us find y prime for each of these points. We start with 0 and 1, and then our goal is to get up to f of 1 with 2 steps. So I'm going to just put a 1 here under the x, and then I'm going to put a box next to this y, or in the spot of this y, because that's our ultimate goal. If we go 2 steps of equal size from 0 to 1, that means I'm going to go from 0 to 0.5 to 1. That tells me that my step size, delta x, both of these spots should be a 0.5. So this is really our starting information. And I'm just going to also write over here again, dy dt equals y over 8 times 6 minus y. And now we'll start plugging in our points. So we'll plug in 0 and 1 into dy dt. Technically, I'm only plugging in y because this isn't even in terms of x or t. By the way, I'll just put t or x here. They're representing the same thing. So if I do plug in 1, I'd get 1 over 8 times 6 minus 1, which is 5. Wait a second. Oh, I'm sorry, I'm plugging in 8. Whoa. Bring it back. This point's an 8. Probably wondering what I was thinking. Sorry about that. Our first point is 0, 8. I got the 8 and the 1 confused. So our first y prime, dy dt, at the point 0, 8, I'd plug in 8 for y, I'd get 8 over 8 times 6 minus 8. And that would give me 1 times negative 2. So this first point here would be a negative 2. Then I multiply negative 2 times 0.5. And that gives me a negative 1. I take that negative 1 and I add it to my y, and my new y value is 7. Now I plug in 0.5 and 7 into the derivative. So now we'd find dy dt at the point 0.5 comma 7. And we'd get 7 over 8 times 6 minus 7. That gives us a y prime value of negative 7/8. If I go to multiply that by a 1/2, negative 7/8 times 0.5 That gives me negative 7 over 16. That negative 7 over 16 gets added to the 7, or we just do 7 minus 7/16, which would give us 6 9/16 as our final answer. So we would say that f of 1 is approximately equal to 6 9/16. Now I know on your answer key, if you look at the other one, they give this as an improper fraction, or it is 105 over 16. Now, how many points for this question? This would be a 2-point question. You're going to get 1 for just your answer and then 1 for the method, which is the table. So that is question B. All right, moving on to C. Question C, write the second degree Taylor polynomial for f about t equals 0 and use it to approximate f of 1. This is a big question on this problem. This is a 4-point question. So real quick, let's talk about the Taylor polynomial for f about t equals 0. If we're going to write this out, our second degree Taylor polynomial is going to be f of 0 plus f prime of 0 times x minus 0, and I didn't have to do the minus 0, but that's where it's centered at. And then our next value would be f double prime of 0 times x minus 0 squared over 2 factorial. So there's some pieces of information that we need here. One of the pieces of information that we need is we need to find the derivative at 0, and we need to find the second derivative at 0. If we can find those two, then we'll be able to fill in the Taylor polynomial. So let's start by doing f prime of 0. Well, f prime of 0 is going to be equal to, this is just a kind of switching up the notation, it's dy dt at the point 0, and then I also have to include that y value that they gave us. When t is equal to 0, y is equal to 8. And if I plug that into the derivative, this is just like basically the first step of Euler's method too, we would get 8 over 8 times 6 minus 8, which gives us negative 2. So that is our f prime of 0, or we can think about as dy dt at the point 0, 8. Now I'm going to do something similar for the second derivative. First, I'm just going to write out f double prime of t, which would be equal to the second derivative at t. So we've got to actually take the derivative of y over 8 times 6 minus y. And this one might be a little bit more tricky. So I'm going to do a little prep work for us. And we know that dy dt is equal to y over 8 times 6 minus y. Well, to make our lives easier, what I'm going to do is I'm actually going to distribute this before I go to take the second derivative. So dy dt would be equal to 6y over 8 minus y squared over 8. Now, in doing the derivative of this, doing the derivative with respect to t. With respect to t, I've only got y, so I need to do some implicit differentiation. So what I would get here is I would get 6/8 times dy dt minus 2y over 8 times dy dt. Now that's my second derivative. What we need for the Taylor polynomial is we need this second derivative at the point 0, 8. And that's what would give us our second derivative at 0. So two different ways to write that notation now. Well, when I go to take the second derivative at 0, 8, notice my second derivative is in terms of my first derivatives. I know what my first derivative is at the point 0, 8. That second derivative, or that first derivative, is equal to negative 2. So I can plug in negative 2 while I'm plugging in 8 for y. So I'll get 6/8 times negative 2 minus 2 times 8 over 8 times negative 2. And when we work that out, we should end up getting 5 over 2. So that's my second derivative. My first derivative is negative 2. Now we can put all this information back into a nice Taylor polynomial. So the final answer for the Taylor polynomial, f of 0, we know that that's equal to 8. F prime of 0 was negative 2, so we're going to get minus 2x. And then our next term, our second derivative over 5/2. I'm sorry, a second derivative, which is 5/2 divided by 2 factorial, would be 5/4 x squared, and that would be the Taylor polynomial for this problem centered at 0. And then we could use, we're not even done yet. Now there's one part left where we have to use this to approximate f of 1. So f of 1 would be approximately equal to the Taylor polynomial at 1, which means I'm just going to plug 1 into this formula. So we've got 8 minus 2 times 1 plus 5/4 times 1 squared. And this answer comes out to be 29/4. Hey, like I said, this whole problem was worth 4 points. I'll show you where those 4 points come from. The first point you get is by finding the second derivative. So basically all of this was 2 points. Evaluating it, finding it, and then evaluating it. Actually writing out your Taylor polynomial, that was a point. And then this approximation right here was a point. So that's our 4 points for that one. All right, finally, on to the last question. The last question seems like it comes out of nowhere. It seems to have nothing to do with this problem at all. It says, what is the range? What is the range of f for t greater than or equal to 0? So, first of all, range. The range is all possible y values. Possible y values that a function can take on. Because it specifically says f, in this problem, our function f is the one that starts at the point 0.8. So I'm looking specifically at this solution. And if we think about this solution, the maximum y value I could have is equal to 8. The minimum y value gets really close to 6 but can't quite touch it. So I'll say the minimum y value is almost 6. But it doesn't quite touch it because we get this horizontal asymptote here. So what we'd say then is that our range is that our y values could be less than or equal to 8, but they definitely have to be greater than 6. And this is either right or it's wrong, and it is worth 1